in just a second. Just want to get that set up first. Yeah. I do have an announcement to make. I figured I could do that while the thing was coming up. Normally, I may have announced this Monday, I don't remember if I did or not, but normally on Fridays, my office hours are 8 to 12 on the Birmingham West Campus, blah, blah, blah. You can look up and see where it is. This Friday, I will not be there. So if you were planning to get in touch with me or touch base with me or something like that, don't even try it. I have an infusion this Friday, and that's going to go from at least 8 in the morning. It probably will. I have to be there before 8, and then it will go till probably into the afternoon sometime. And at that point, I drive home and go to bed because the Benadryl knocks me out. So, anyway, that will be, I will not be on campus, either campus on Friday. So I just want to let you know that. All right, any questions on anything we've covered so far? Okay. We're in Chapter 7, Applications of Integration. The first one we had was areas. That was in 7.1. And now we're doing volumes. And 7.2 is talking about the disk method of doing volumes. And example 4 we did last time. However, example 5 is not on the slide set, so we're going to go from here. Let me get my pen set up, and we'll go from here. But even though it's not on the slide set, if you want to see an interactive version of this type of an example, it may be exactly this one or one like it, you can go to larsoncalculus.com. Don't need a passcode, don't need anything else. All you need is a computer here with the internet. Go to larsoncalculus.com. You'll have to find your way through it, but y'all are used to doing that, so I don't think that'll be a problem for you. All right. Now, what we have here, a manufacturing problem. A manufacturer drills a hole through the center of a metal sphere with a radius of 5 inches. That is, I was going to say that is a confusing sentence that says, as shown in the figure, so they did have a figure, but then they say the hole has a radius of 3 inches. Because even though of radius 5 inches was closest to the metal sphere, that's what I would have assumed it was, but since they hadn't yet said the second sentence yet, I didn't know if that was the radius of the hole or the radius of the sphere. But the second sentence cleared that up. The hole has a radius of 3 inches. What is the volume of the resulting metal ring? Okay. And it wants the entire volume. Okay. Now, one way to do that would certainly be to calculate the radius of a sphere. Okay? But then, to try to get the volume of a sphere, okay? You knew the radius. The volume of a sphere, but then to get the volume of the hole is a tougher issue. Now, if that was a cylinder out of it, that would be easy to do too. But this has those caps at the end. And that would not be an easy thing to calculate because they're not there, So, that would give you an approximation, but it wouldn't be exact. Okay? Now, what they suggest here, and it certainly works, okay, is to draw in a two-dimensional plane what you've done there. Okay, in other words, okay. If you imagine that sphere to be centered at the origin of a three-dimensional plane, okay, and your hole is going through down the x-axis, down the x-axis, centered at it, okay, then, and do the cross-section in the xy plane then, you would have just a little kind of a wedge at the top, okay? And you're going to revolve that around. That's how we're going to find our volume, okay? Even though the sphere was an easy thing to determine the volume of, that cylinder that you took out with curved ends was not easy to calculate. So, in fact, you would have to almost do the same type of a figure at the end to do those, and that would be easy at all, okay? So, let's pretend, sounds like pre-K, doesn't it? Okay. We're going to have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay? So here's going to be our cylinder, our sphere. Don't worry about it being ugly. I'm going to erase most of it later. Okay. Our cylinder, like thing that we're going to drill the hole, has radius 3. So that's going to go here to there. Okay. So this is all we're interested in now, is this part here. Okay. I tried to outline that because now I'm going to erase everything else. Okay. Didn't do a great job of it, but let's see, I can get rid of that one. Okay. So that's what we've got. Okay. Now, bless you. Okay. Does that make sense? Okay. Now, what we've got to do is find these two. Oh, I almost erased everything. Duh. These 2 points of intersection. Where is it that those two are equal? Okay. So we want we know this is 3 here, okay? We know the y coordinate is 3. We need to find those x coordinates there, okay? So we have, if we draw I guess that triangle would be adequate there. This is 3, and this is 5, right? Because that sphere had a radius of 5, and that's on the edge of the sphere. We can calculate what the x is, right? What would that be? 4, exactly. And this will go to -4. Mine's almost lining up right. That's amazing. Okay. So that would be 4. Okay. I'm not sure theirs lines up much better. Okay. Now, next thing we have to do, so we know our limits now. Okay. Now, as you may have realized by now, I'm lazy. Okay. So I don't like to do any more than I have to. So the volume of this half rotated around is the same as the volume of that half, right? So I'm really just going to go 0 to 4. Okay, and then double it. Okay. Is that all right with you? You don't mind being a little lazy? I don't mind that. Okay, good. All right. You'll live. I don't know why I'm not getting this. I know they're ready, but like. Okay, say it one more time. I'm not have to say anything yet. I was trying to figure out why it's 4 because. Oh. It's supposed to be like a hypothesis. Square, okay. This square plus that square equals that square, yes. Right? Okay. So 5 squared is 25 minus 3 squared is 9. That's 16 squared root of that is 4. Okay. Now, harkening back to our favorite little 3, 4, 5 triangle. I don't know if you remember those. My dad was an ag engineer, but he didn't work as an engineer, though he used his engineering a lot. He was a farmer, but he had his degree in ag engineering, but he liked farming, and he didn't want to work for anybody else but himself. So those two combinations, he farmed. But then we built our own sheds, and did most of the work on our tractors and all the other things. And when we built the shed, he used 3, 4, 5 triangles all the time to make sure that the base was square and stuff like this, using 3, 4, 5 triangles. So I grew up with 3, 4, 5 triangles. So to me, it's patently obvious, but you probably didn't. But that's my favorite triangle in the world, is the 3, 4, 5 right triangle. Yeah, so I knew it as soon as I saw the dimensions. That had to be a 4 up there, without even looking at the picture to see if, well, is that a little past 4, a short of 4, more than 4? Yeah, nope, that's the 3, 4, 5 on the nose. Okay.
How would you use that to make sure something's square?
Okay. If you get a rope that's at least 12 feet long, okay, and measure off 3 feet, from that point 4 feet, and the rest of it's 5 feet, have, he had 3 sons, so 2 of us, all we had to do. He held one and laid out the, had one person here, one here, one here. That's 5. The only way you could get that to be that, this has to be a right angle. So you lay it out.
Oh, okay. Yeah, that's what you're saying.
Yeah, had to be. Okay.
I'm a machinist, so I
Yeah.
really enjoy making sure things are square. That's what
Right.
I was just trying to figure out how that meant that something was square. That's what you're saying now.
Yeah.
But if you're short, then that's going to be longer than 5 feet. If you're wide,
Yeah.
then it's going to be less.
Yeah. Right. Yeah. Okay. And he did it in other ways too, but yeah. Making, he had squares, and other things too that he measured things, but if he ever needed to check something, 3, 4, 5, he, like the end of a joist or something like that. Yeah. Okay. So we're just going to go 0 to 4 and double it. Okay. Now, the question now is it better to do dx's or dy's? My inclination right now is to do the dx's, okay? Unless y'all have any gripes the other way. Do you?
No.
Okay.
I was only going to say DYs before because I thought it would have more space, but you're saying DX is better?
I think they probably both are okay. You're just probably going to have to do a little more manipulation with the dy's, but maybe not. Let's just see if I don't like the way this is looking. Okay. Now what we're doing, we have to get this length here, from here to there. We're not interested in here to there. We know that's 5, okay? We need this here. Well, again, the ratio here is 4 to 3 to 5. Well, no. Is that right? No, it isn't. Wait. Is that? It's not the length being that, but the ratio. Is that the same? We know the right angles are the same. Okay. We don't know that this is the same, but the no, I don't think we can say that, can we? Yeah. Let me erase that thought from your brain. Okay. Whoops, I didn't need to erase the delta y. Okay. I mean delta x, dx here. Okay, let's think through this for a moment here. Okay. Okay. Let's do the whole wedge there. That one I know okay. Any point here on this sphere is going to be x squared plus y squared is equal to 5 squared, right? Every point on there, okay? So that means the y is equal to the square root of 25 minus x squared. Yeah, that's going to be true. Okay? So that's going to be the height there for any x between 0 and 4. That's going to be the y. Okay. Now, that's going to be the outer part. The inner part, of course, is just going to be 3. So we're going to subtract that off. So I think that's our washer then. And then we're going to do that from 0 to 4 and then double it. Okay. So the wedge, as you rotate this around the x-axis, okay, then you're going to have a washer. Well, let's start with a disk of this radius. That's going to be your, what we were calling capital R before, okay? And it's going to be pi times that R squared minus pi times 3 squared, because that's, the 3 is constant there, right? That height is 3 all the way here, okay? So that will just be that. So that'll be minus 9 pi. That's always going to be the second part of it. For whatever value x you have, 0 to 4, okay? So that should be our volume, okay? The volume should be pi, just like it always was, integral from 0 to 4. Oh, let's make it 2 pi because we're going to double this. Okay, 2 pi, 0 to 4, I keep wanting to write the pi again. You don't need to write the pi again. Here's your radius, and when you square that, that's going to be 25 minus x squared times, minus 9 pi. 9. Factored the pi out of there. Okay? And then your dx. Okay, I believe that's right. So that's going to be 16 minus x squared. So this would be v is equal to 2 pi times the integral from 0 to 4 of 16 minus x squared dx. Okay? The calculus is the easy part. Setting up the problem, that's where the difficulty is. So let's do the math there. I'm going to erase some of this so it's not in our way. Okay. Okay. 2 pi times the antiderivative of 16.
X.
16x. Right. Okay. Minus. Second, x cubed over 3. Okay. We'll evaluate that from 0 to 4. Okay. It's going to be 2 pi times. Okay, what's 16 times 4? 64 minus 64 thirds, right? Well, 64 thirds is 1/3 of 64, so this is minus 64 thirds. So what's going to be in here is 2/3 of 64, right? That's a weird way to do it, but 2/3 of 64. And that's multiplied by 2 pi. Okay? So that's going to be 128 doubled is 256 pi over 3, I think. Okay? Oh my goodness. 256 pi over 3, and that would be cubic inches, because they did give us as inches, didn't they? Yeah. Okay. All right. See how that works? Or was there any magic in that you don't understand? I'm sorry I did the calculations in a strange way, but I basically factored out a 64, and that left us 1 minus 1/3, 1 and 2/3. To me, that was easier than common denominators and that kind of stuff. I'd have to multiply 64 by 3. I didn't want to do that. I'm way too lazy for that. So factor out the 64, and you left with 1 minus 1/3, and that gave you 2/3. 2/3. Make sense? I'm sorry if I do things strangely, but I figure you knew how to do the other way. I thought, let's just be lazy and do it that way.
Makes sense, though.
Yeah. Again, it was the easiest way I could think of doing it, so it may not be the easiest way, but the easiest one I can think of at the moment. The key here is one of the pieces. That's the radius of the outer part, but you're going to square it, so you lose the square root symbol. So that's just that. And the radius of the inner part is always 5. It's always 3. And we pulled out the pi. So you doubled it because we just went 0 to 4. If we went minus 4 to 4, that would work fine too. Just more work. I always like evaluating at 0. It's one of my favorites.
Definitely an easy one.
What's that?
Definitely an easy one.
Yeah. But it has to be symmetric. It has to be even. So you have to be able to do that. All right. Got it? Okay. Let's move on to solids with known cross sections. Okay.
We're not going to do example 6.
What's that?
We're going to do example 6 and 7.
Well, that follows, doesn't it?
Oh, does it? Oh, I'm sorry.
Yeah, solids with known cross sections here. Okay. Expression that hurt. Stand up. With this method, you can find the volume of a solid having a circular cross section whose area is A is equal to pi r squared. Okay. I classify that as a cylinder. This method can be generalized to solids of any shape as long as you know a formula for the area of an arbitrary cross-section. Okay? And here's this. Okay. All right. I didn't mean to say this to her. I'm glad I'm thinking of it now. I'll wait till somebody else comes in. And here's Daniel. Okay. For this class, unless something was turned in today, I think I'm caught up in the grading. However, what I'm not is caught up in Blackboard, okay? Because I have, first mini-term I had 2 really big classes, 1 pretty big classes, and then these smaller classes. Second mini-term, now I have 3 big classes and these other smaller classes. So, and also, huh? Yeah. Well, I've got a lousy department chair. That's me. Okay. I'm my own department chair. Okay. But anyway, yeah, okay. So, all right. Now, but the thing that's really messed me up is not just that, though that contributes to it, is we have been working on spring and summer schedules. They were a mess. They were just terrible because what we're doing this year, what we did for fall term was institute a brand new way. We eliminated the Math 090 course that we had, combined it with 098, which was bad enough, took some of the people who would have been in 098, moved them to 100, and then just all the 090s and most of the 098s would have stayed in 098. Some of the 098s and the 100s. We changed and revamped it, and we went to a new book and everything. And then they started these labs, these co-requisite labs. And anyone who didn't have the scores, well, everybody in 098 had to go to a lab section. So they became 4-hour courses, effectively. And everyone who was in the 100 courses who scored that would have been in 098 before, they have to go to the labs. Okay. So that makes for a real nightmare in schedule, trying to do schedules, because you can't predict how many people are going to be needing labs or not. So we have to provide labs for enough people, and we don't. And we have one designated lab for both 098 and 100, and it just gets to be a nightmare. Well, we did it one way this fall, which most of them thought was crazy, sort of shotgun labs. Just put a lab out there for every hour of the day, and then students signed up for any lab they wanted to, no matter what class they were in. So that meant the lab supervisors, people were coming in at different points in their classes, and it was a mess. And then people weren't showing up for labs and stuff. So for spring, they decided to do it differently and have the labs tied to the courses, okay, which makes more sense, but that takes up more time because they're 1-hour labs, but you fill it in and it takes up an hour and a half space, so you have extra half hours that no one's in the lab. And so we don't have enough space for the lab. So anyway, it's just been a nightmare trying to juggle all the pieces and not knowing how many people are going to which classes. So I'm still working on spring schedule. I should have been through with it a couple weeks ago, but it was such a mess. But I'm getting closer to being finished. So that means all the times in my office are spent working on schedule and hardly any. The only time I have to grade are the 4 classes, when I come in here and I can't work on the other, or when I'm at home. And basically, since my classes are so late, like last night, I got out of class on Tuesday and Thursday, 7:45. I don't get to leave campus until 8. I don't get home till about 8:45, eat supper, and then try to grade a few papers. And besides last night, I had phone calls and other things we had to take care of. So I get any grading done last night. So that was my sad song. Okay, the violin music was beautiful, wasn't it? Okay. Yeah, exactly. Okay. So, sorry I don't have your grades at Blackboard. I do have things graded if you want to see your papers, but I don't have them at Blackboard yet. But that's one good thing about the infusion on Friday. Okay? I'll sit in the waiting room for quite a while. I'm grading like crazy while I'm in there. And then they take me back to the infusion room. I grade like crazy for a while. But then at some point they give me the Benadryl, and I've got about 15 minutes of lucidity before I'm la-la land. So I don't do much grading after about a half hour after the and then the rest of the day is not very good for grading either. But at least I have some time that generally I'm not bothered by anything else. So maybe I'll get caught up some on grading. I can't work on schedule there. I can't put things on Blackboard most of the time either, because even though they have a Wi-Fi there, everybody else is on it and you get kicked off. I can't ever count on that. Okay, so anyway. I don't know why I thought of that after the minutes came in, but I did. Okay. I think I just graded senior score. Well, I don't have those. I didn't like that. Okay, anyway. So this method can be generalized to solids of any shape as long as you know a formula for the area of any arbitrary cross-section. Some common cross-sections are squares. We know that area. Rectangles, yeah, that's pretty easy too. Triangles, yes. Semicircles, yes. So, I don't know why they're blah, blah, blahing on this so much. So here are some of the volumes of solids with known cross-sections. For cross-sections of area A of X, taken perpendicular to the x-axis, the volume is equal to, this is perpendicular to the x-axis, the integral from A to B of A of X dx. If you can write that expression of the area of that cross-section as a function of x, you got it right. For cross-sections of area y taken perpendicular to the y-axis, then you would go from C to D, you know, a sub y dy. Okay? Now, let's see if we can break this down a little bit better. Okay? Now, here is some shape. They haven't told you what that function is that makes that shape. But here's the shape. And if you can do a dx here, and then do these cross-sectional things here, the thickness is dx. That's piece of cake. If you can determine that area, okay, based on what we know, it's sort of like what we just did. We knew the area of a circle, and we knew the the thing that came out of it. Yeah, those were pretty easy to do that thing. So if we do this area here as a function of x, I'm not sure I would. That shape doesn't look at all familiar. It's curved up here, straight here, and here. I'm not sure I would know that. Okay, so but if you did, that's how you would do it. However, that doesn't look very promising to me. But that same shape, let's do the dy here. Well, look at that. That's a rectangle. I can handle that. Okay. Oh, is it a rectangle? Yeah, it is. Yeah. That's a straight line here, straight line here. That would be far better to do dy's there. You want to do that in the previous one. And maybe it would have worked okay, but this is certainly doable there. So that would have been the one for this one. But yeah, I don't know this area as a function of x. I do know that area as a function of y. But I'm saying if I can figure out what the ratio of the angles go, and if they gave you enough information, you could do that. I'm not sure I could do that. Okay? So here's example 6. You wanted it, you got it. Toyota. Okay. Find the volume of a solid shown in this figure. Okay, thank you for drawing the figure for us. The base of the solid is the region bounded by the lines of f of x is equal to 1 minus x over 2. So this line right here, the y here is 1 minus x over 2. So the y is always exactly back off. As x increases by 2, y, the f increases by 1. So it's that. And so that's your line there. Okay? The g of x over here is minus 1 plus x over 2. Okay, that's this line here. See, this one has, you have to sort of twist your mind here a little bit. And if you look at this, this has a negative slope. There's your y-axis, this is your x-axis. Your decrease, as x increases, your y value is decreasing at a 2 to 1. So that's where the minus 1/2 comes from. Y-intercept is plus 1. Okay? Over here, y-intercept is minus 1. And this, again, looking at this line going up here, xy plane, take this and do it like this, that would be an increasing slope, going from minus 1 to 0 and 2, so that's the slope of positive 1/2. So that's that. The base back here is x equals 0. Okay? So, here you have function of x, and y is equal to x equals 0. I'm afraid to admit that. Okay, now, they say the cross section here are equilateral triangles. Can we square to that?
Yes.
They didn't tell us anything in Z, okay? They're just telling us the cross sections are equilateral triangles. Because, I mean, this could have been a real shallow thing here, a real steep thing. They're telling us that is equilateral triangle. We know the base is the same on this side as it is on this side. And they're saying this is whatever it takes to make those two sides the same. Now, they didn't say that unless they said it in the book. They just showed us in the picture and said the bases, the cross-section are equilateral triangles. Okay? Not going to argue with it. Okay? That's what the cross-section is. Okay. So, you have to know a little bit about equilateral triangles, like what their areas are, in order to do this, but it's certainly doable. So the length of each side is, your width, thickness is delta x. The way they set it up here is delta x. The length here is from here to here, so it's this thing minus that thing. And that's quite doable. Okay? It's really easy to do. Okay? Let's do it. The length here, that length here is 1 minus x over 2 minus a minus 1 plus x over 2, which would be a 1 minus x over 2 plus 1 minus x over 2, which would be 2 minus x. Right? That's the length of that. 2 minus x. Okay. So we have the base of the triangle. Okay. Now, because it's equilateral triangle, the area of that equilateral triangle is this. Now, the thing is, this one's not an equilateral triangle. It's this thing right here that's the equilateral triangle. Okay, we're only seeing the base of it. Okay, so let's picture this one. So I'm going to draw this equilateral triangle on, that's not a good start, is it? On the Z Y plane. Okay? Okay. Looking back at it this way, where this up here is going to be Z, and this is Y here. Okay? Now, we know this length here, that's this thing right here. That's your length here we just did, 2 minus x. Okay, so this is 2 minus x. And this is 2 minus x. And this is 2 minus x. Because it's an equilateral triangle, right? What is this height here? Well, equilateral triangles are also equal angle triangles, right? With this being 60, 60, and 60, isn't it? Only way to have equal angles be 180, 3 and the 180 is 60. They always have to be. For equilateral triangles, they're all 60 degrees. Which meaning half of this one is a 30. And half of this is, the other half is 30. So let's just take one side of this. Okay? This is 1/2 of this, which is 1 minus x over 2. Right? That was right there anyway, right? Okay? And that's, if you'll allow me to regress just a bit. What if this was just 1? Then this would be 2, right? Because that's exactly half of that. This has to be the square root of 3, isn't it? So this height is the square root of 3 times the base, okay, times half of the base, times that. So the height is square root of 3 times that. So that would be root 3 minus, well, root 3 times 1 minus x over 2. Why make it more complicated? That would be what it is. Root 3 times 1 minus x minus 2. Okay. So now we know the height, and the area, the area of that triangle would be 1/2 the base times the height. Okay? Where the base was this, and the height was this times this, which is half of that. So basically, it's root 3 times 1 minus x over 2 squared. I know that seems bizarre, but it is. 1/2 the base is that, and the height is root 3 times that. So 1/2 the base times the height is root 3 times half the base. Squared. Half the base. Now, I'm not sure that's how they do it. It's not how they do it, but it comes out being the same thing. So what is the volume then? Messy. The volume of the thing would be the integral, summation, all those up. Now the root 3 is going to be in there, so let's pull the root 3 out. Okay? And you're going from 0 to 2, because you're doing dy's here, aren't you? No, dx is here, okay? And doing 0 to 2 on y, on x, okay? 0 to 2, yeah, times 1 minus, okay, let's go on and square that thing, is that okay? All right. So that would be 1 minus x plus x squared over 4. Check and see if I'm right here. Let's square this. Square the first, twice the product of the 2, twice 1 times x over 2 would be minus x. So there's that, and then plus this thing squared. So that's what we're squaring. Integrating. 1 minus x minus plus x squared over 4 dx. Okay. It's that area of that thing that we just said. Here's the area of it. Integrated from 0 to 2. That incremental area. Thickness is dx. So let's see what that would yield. Volume is equals root 3, antiderivative of 1. Help me. X minus x squared over 2, right, plus x cubed over 3, but then you got a 4 down there, so that would be x cubed over 12, right? Right? Evaluated from 0 to 2. If you do the 2 part, I'll do the 0 part. Okay? The volume would be the square root of 3, I can't talk, times 2 minus 2 squared is 4 over 2 is 2. That adds a 0. Plus 4 cubed, 2 cubed is 8 over 12. I did the 0 part, and that's nothing. So this would be 8 over 12 is 2/3, right? So that would be 2 root 3 over 3 is what I get for the volume. Let's, oh my goodness gracious, that's what they got to. The wonders never cease. Okay, now they did their math approach a little differently from what I did, but we got the same answer. Okay? Want to see how they did it, or do you want to leave that up there a little bit longer? It's kind of a mess in there. Sorry about that. But to me, I needed to draw a picture to describe why all these things were happening. Everybody got it? Are you still getting it? It's on page 460, top of the page, example 6. The way they approach it, you might find makes more sense. If so, go with it. You know, it's fine. I'm not offended at all. Hurts a little bit, but not that much. Got it? Everybody? Let's see how they approach it. The base and area of each triangular cross-section are as follows. The base is, okay, all they did here was subtract one from the other just like we did. The length of the base was 2 minus x, right? That's what we got, right? The left side minus the right side minus left side, whatever, okay? 1 minus x over 2 minus 1 plus x over 2, which basically is plus 2 minus x. Okay. Now, the area of an equilateral triangle, they come up with this formula, which I never memorized that formula. I'm not even sure I've ever seen that formula before. It has to be true because it gave them the right answer. But it's, if you think what we did, I took half of the base of the right triangle, okay, and then did the root 3 times that, and double the base, okay, so I had a 2 in there, twice the base squared times root 3 is basically what I got. And they did this base, which was half of that, okay, but then when they squared it, no, I'm sorry, that base, which was twice what I was using, so when they squared it, they gave it the 4. So the 4, that's why they had to have the 4 there. I didn't have to have the 4 because I took half the base. But anyway, we came up with the same thing. It doesn't look like it's the same thing, but it is. Now, the advantage of theirs is they don't have a fraction in that square, the binomial square, which was a little messy, but it wasn't that bad. But you had to know the formula. And I didn't know that formula. I probably could have derived it, but the way I did it, I came up with a formula. So basically, my 4, therefore here, I had over 2 in here. Because when you square this, you get 4. Put a 2 in here, that'd be 1 minus x over 2 squared times root 3. That's the same thing they have, but I derived it from the other, from first principles, you might say.
There's also other facts.
What's that?
I said, okay, because that's what I was on the ask you. You say you could have derived the formula that was in actually. How would you have?
Yeah, you would have to go through all that I just explained. Now, I came up with the same thing, but I just didn't have the 4 on the outside. I had a 1/2 on the inside. And it comes out the same thing, okay? But by pulling the 4th out, then it left you with that, and that's easier to do, except now they go back to this, 0 to 2, which is what we did, of that area, which is that, no reason to have the root 3 over 4 inside, so pull that on the outside, then evaluate the integral. Now they did it separately here too. Rather than expand the square and then integrate the pieces, they integrated that as a thing, and that would be that thing cubed over 3, but then chain rule had a minus 3, so you had a minus out here. So that, to me, is a lot more complicated than what I did. But if you are happy with it, go for it. I would tend to forget about that minus sign, okay? So you do that and you get square root 2 root 3 over 3. It comes out the same thing. To me, that calculation see, when you put the 2 in there, 2 in here, that'd be 2 minus 2, 0. So that was 0. And then put a 0 in here. That gives you two cubed is 8 thirds times this, yeah. I don't see where the, oh yeah, because you're subtracting that off. That's where the minus sign gets canceled out. Because you're subtracting that. It's minus this, so minus and minus like plus. Yeah, and you get the same thing. I'm not sure. I like my method just as well or better than that. Okay. As long as you do all correct steps, you should get correct answers, right? And they did, and I did. Okay. They don't show example 7. So let's us do example 7. Hopefully it won't be as bad. Okay. Application to geometry. Prove that the volume of a pyramid with a square base is V is equal to 1/3 HB. Okay? Where H is the height of the pyramid and B is the area of the base. So I already said the base is a square, so that's just going to be x squared. I guess x is whatever, yeah. Okay. Maybe I shouldn't use x because that may get confusing. They just call it b squared. Okay. Okay. Where h is the height of the pyramid and b is the area of the base. Okay. So unfortunately you have to draw a picture, and since we don't have a picture here to look at, yeah, I've got to draw one. Okay. Now they like ignoring the z-axis completely. They're making the y-axis, and this is the x-axis, but they do give it a little bit of a thing here. Okay, so let's just say that's our square base. Okay, that's supposed to be a square at an angle. And your height is up here somewhere. Okay, so you have lines going down from the height to all of your bases there. So many lines. Okay. Now, if that's a square base, every cross-sectional area, and by the way, this time we're going to be doing dy's, because the y is here, so this is going to be our dy. So we're going to have, got too many lines in here. Let's do this, that. Okay. That's the one, and the dy is the thickness of that. Okay, and that's not very level either. All right, now, all those are little squares going up that because that square base continues all the way up. Just changes its dimension. Okay? This is the h, the height of that, and this is the little b is the base of that. Now, whatever your ratio of height to base is here, that ratio carries through all these. So the base here, they're calling b prime, and the height here was h prime. And those ratios are always the same. Okay? But they don't call it h prime. They actually say what it is. You need everything in terms of y because we're using dy's. Okay? Now, so let's just do a cross section of this. So this is y. This is our h up here, the height. Here's our x over here. And okay. Here's something we have to deal with here. Here you're going from minus b over 2 to b over 2 because the whole length here is b. Okay? Same thing here. The y's, well, they don't give you that dimension. But anyway, so let's look at this little triangle here. Okay? And this is the y-axis, by the way, the thing's going up. So at whatever y you are here, this is y, how far you are from the x-axis. And y is going from 0 to h, by the way. Okay? So that's where the h comes into play. Now, let's take this one at the bottom here. That triangle right there. Okay, it's not going to any corner, it's going to this. This is b over 2, right? And this is h here. Okay. So the ratio of the height, which is along the what I was calling our b prime and h prime. B prime is to h prime, okay, as h is to b over 2, okay? You see at the very bottom here, this triangle that goes from h at the top out here, since this is b minus 2 minus b minus 2 plus b minus 2, this is going b minus 2 here is h. Oh, I said it backwards. Yeah. Can't believe I did that. B over 2 is to h. Okay. Got to have length to height, length to height. Okay, they have to be the same thing. All right. So, this h prime that we were talking about here is h minus y. Remember? We said that this h prime here, this height prime here, that I called h prime, that is y, h minus y, whatever the value is. So that's where you get, so you get your b prime over h minus y is equal to b over 2 over h. That ratio is the same. So that means that b prime, okay, is equal to, let's simplify this as much as possible, b over 2h, that's what that becomes, times h minus y. Okay, strange, weird, but I think that's true. Okay, so now we know the base, and we know the height. Okay, so the area is this thing squared. The area of that slice here is this thing squared, because it's a square. Okay, so that's what we're looking at. A as a function of y is equal to this thing squared, which is that. Okay, I think we've got our formula now. Let's see if I can erase some of this mess stuff and see if we can do our magic here with that. All right. All right. All right, so your volume is equal to, I'm probably going to pull some stuff out. I know, okay. No, okay. All right. It's the integral from 0 to h along y. Don't have a dy here, that's the thickness of it. And then the base of any one of those segments there is this thing. So that's going to be the little b over 2. I think we can pull the h out too, because that's fixed. And then what's in here is now h squared minus 2hy plus y squared. That's just that thing squared. Oh, wait. That's a b squared over 4h squared, sorry, because that was squared also. That's what gets pulled on the outside. All right, so b squared over, yeah, sorry, I know, I changed.
What does the bottom part say?
Yeah, that's 4h squared. It's this thing here that doesn't have a y dependence. I pulled that out, but I forgot that it was squared. So it's b squared over 4h squared. That's outside. Okay. And what's inside is, well, let's go on and evaluate the integral. Okay. Okay. What's the integral of x squared? That's just a constant, by the way. With respect to y. H squared, no, h squared y. Later, when we evaluate it, it will be h cubed, but let's not evaluate it yet. That's just a constant now. Minus the 2h are there. Now you multiply that by y squared over 2, right? 2h is your coefficient, and the integral of y is y squared over 2. And then we have a plus y cubed over 3. Right? Okay. You're evaluating this from 0 to h. And you were absolutely right. I hope I can erase my figure. It's ugly enough I ought to be able to erase it, but I can't go back and look for where I might have made a mistake if I did mine. So whoops, I shouldn't have erased that h. That was the wrong h to erase. Okay. Now, the volume is equal to b squared over 4h squared times, and this will be h cubed minus that 2 and that 2 go out, and that's another h cubed, isn't it? Okay, should have erased that, but I didn't. Plus, and by the way, these are going to divide out to nothing, and this will be h cubed over 3. And the zeros would not produce anything. And I'm not getting the same thing they did.
Where did the
Okay. Yuck. Yeah, there had to be an easier way to do this. Okay. They set up the ratio, which I've almost erased now, of b prime to b as h minus y is to h. And it's kind of what I had at one point, except I had an over 2 in there that may have been throwing me off. Maybe I didn't need that, except they introduced it someplace later, so maybe I was okay. So b prime was b over h times h minus y. That would have made things a lot simpler. And the area of that was just b prime squared, which is b squared over h squared times h minus y squared. And again, they do a weird, oh, I think I was okay. I think except for the 4, I'm perfectly fine. I shouldn't have had the 2 in there. So if you take that out, I think I'm in pretty good shape. Let's see what we get. Yeah. You get 1/3. And the h squared here cancels that out. And you get b squared h. What's b squared? That is your capital B. I wrote down 1/3, 1/2. That's one thing that was throwing me off. I wrote down the wrong formula. It's 1/3 hb squared, hb. Yeah, we got the same thing. I just shouldn't have been using b over 2. I should have been using b, because that was the base. I tried to multiply by it, but I did it the wrong way. So yeah. We did wind up with the same thing, believe it or not, if I'd have used the b rather than b over 2. Okay. You do use b over 2 at one place where you plug in, but that comes out in the sauce, I think. So, all right. So anyway, basically almost had it. I just put b over 2 rather than b. It would have been fine. Homework exercises here. Do either 5 or 7, or both. They're both at Calc Chat, 5's at Calc View. Do either 9 or 11, they're both at Calc Chat. 9's at Calc View. Do either 13 or 15, they're both at Calc Chat. 13's at Calc View. Do either 17 or 19, they're both at Calc Chat. 17's at Calc View. Do either 21 or 23, they're both at Calc Chat. 23's at Calc View. Do any of the odds 25 to 31, they're all at Calc Chat. Either 33 or 35 or both, they're both at Calc Chat. Either 37 or 39, they're both at Calc Chat. 37's at Calc View. Do any of the odds 41 to 47, they're all at Calc Chat. 49 or 51, they're both at Calc Chat. If you want to explore the concepts and try 53, you can. I'm thinking it's at Calc Chat as well. And then comparing volumes, that's 55. It should be at Calc Chat also. Okay? Now, dividing a solid. Try 57. That should be okay. And then you have some word problems. Applied problems, whatever you want to call them. Any of the odds 59 through, goodness gracious, I think I would say 59 through 69, okay? Because 71's sort of one of those think about it, so you can think about doing it if you want to. It should be at Calc Chat. Now, 72 is not one you have to do, but I want to point it out to you because it has a person's name in it. Cavalerius, or something like that theorem. You could write on who in the world he was, or how did he come up with this theorem, various things like that. It's an interesting problem, and a, sort of an amazing result. But anyway, you can, I only mention it so you could use his name or the theorem if you wanted to do a paper topic. And then 73 or 75, either one, they're using cross sections. 75 looks like a real bear to me, but I haven't looked at it closely. 77 would then be one you could try too. All right. That ends 7-2. All right. Let's move on to 7-3. How much time do we have left? Oh, we have plenty of time. Second? Plenty of time. Okay. So let's end this. And now move to 7-3. We've done volumes using disk method, and it may have led you to think this is the be-all and end-all and the answer to doing volume problems. It's not, okay? There are some problems that will just not work very nicely at all with the disk method. You might be able to force it to work, but it's not going to be the nicest thing in the world. So sometimes we want to do another method, and this is called the shell method. We'll find the volume of a solid of revolution using the shell method and compare that with the disk method, the two of those methods beside each other. Some problems work equally well with either one. Other problems are almost exclusively one or the other, okay? So you sort of need to know the difference. Now, here's what we're going to do. Alternative method for finding the volume of a solid of revolution is called the shell method because it uses cylindrical shells. Okay? Comparison of the advantages of the disk and shell method given later at the end, basically. Consider a representative rectangle, as shown here, where W is the width of the rectangle, this little thickness here. Later, that's going to be our dy, dx, whatever, depending on the orientation of this. And the height is the length of that rectangle. I would thought of calling that the height with it lying down like this, but I guess that would be fine. And p is the distance between the axis of revolution and the center of the rectangle. That's sort of like our radius that we were Okay? Now, they introduced sort of a weird kind of a thing here to talk about the inner radius and the outer radius, where P is the average radius, and this would be P minus W over 2 and P plus W over 2. And guess what? Once you get the W to be incrementally small, it's not going to matter. So I'm not even sure why they introduced that at this point. Okay? When that rectangle is revolved around the axis of revolution, it forms a cylindrical shell, or a tube of thickness W. Think dx later, or dy later. To find the volume of this shell, consider the two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell, radius of the smaller cylinder to the inner radius of the shell. Because P is the average of those two, you know that the outer radius is P plus, this is what they're saying, outer radius, inner radius. Okay? Now, the volume of the shell is the difference between the volumes of the complete outer shell, cylinder, minus the hole that you cut in. So that would be pi, and this is the outer radius, P plus W over 2 squared times the height, minus P, that's the hole you cut out of. It's the whole shell, the whole disc, and then cut out the inner disc. Okay? Now, if you were to do the math here, which I hope you do, it's P squared, okay, plus twice the product, so it would be 2 times W over 2, so that's just going to be W times P, so plus PW, plus W squared over 4, okay, times H, all that times H, minus this. Now the pi and the H are all the same. It's pi r squared. That's the area of the outer base and the inner base, that kind of stuff. But you see, pi P squared H, this is going to be a minus pi P squared H. Those are going to go away. The only thing that's contribute is the pi. When you twice the product here, you have a plus PW here. Here you have a minus PW. So that's going to be minus a minus, which is going to be a plus. So you're going to have 2 of those. So 2 pi PWH. And whereas the last one, this is going to be a plus W squared over 4. That's going to be a plus W squared over 4. So those are going to subtract away. So you just have the cross terms, which is 2 pi PHW. What is a P? The average radius. The H is the height, and the W is the thickness. All right. Now, if you let your thickness go to your dx or dy or whatever, then the average radius is just going to be the radius, P. Okay. And the height is going to be height. You can use that formula to find the volume of a solid revolution. Okay. For instance, here's the plane region of 728, which is that figure right there, revolved around a line to form the indicated solid. Okay, here's what we got. We've got this triangle here, the light blue triangle, revolved around the x-axis here, and that gives us another Christmas tree base. Okay, solid cylinder hole in the middle. Okay, that's that, and then a triangular region around like this. No curves in it, just very plain. Okay. Sometimes they call that the frustrum of a cone with a hole in the middle of it, whatever you want to call it. Okay. Now, if you were doing the disc method, you would be doing dx's here, okay? And the dx's, you would have to have that thing. Let's not do that. We'll think about that later. This time we're going to be doing dy's here, if that's your y-axis. And what you need to know is the radius here as a function of y. Okay? Because those are going to be your delta y's, dy's, ultimately. So, consider a horizontal rectangle. That's this rectangle here. And just picture that as here. Wish they did a cross section of it, they don't. But this would be, say, this part right here. And you see there's the day, there's just that little portion of it. Okay? So that rectangle. The width is delta y. The length is that h of y. Okay? Now, okay. If you had this triangle, we know what this is, y is equal to c here. This line here that we have interested, we could say if that was indeed the y-intercept, then, and this was your slope here, you could get y as a function of x, and then solve for x, and that's not a hard thing to do with a straight line, and you get x as a function of y, and the x would be your h here. You see, the x is how far from the origin you are to here. So that would be what your h is, and have that as some function of y. This is not a particularly great one to use as an example, but it does work, okay? Then what we just said, the volume is 2 pi times that radius function times the height function. These are both functions of y because you're doing your delta y here. Now, I don't know why they take you through all this, but that indeed does generate a shell. Now, here's the way I think about it. I'm not sure this is any better, okay? Completely different issue. The h is a function of y. You got to figure that out some way, right? Okay, this rectangle is area, that height, that length, I like to call it a length, not a height, that length times your delta y, or your dy, ultimately is what it becomes. And what you're going to do is take that area and rotate it about that region. Well, the rotation around there, just think of this as a circumference. And the circumference of this there is 2 pi r. That's your r. So 2 pi r times the area, which is length times width. 2 pi r length times width. That to me is an easy way to remember this. And the rest of it is just, I guess that's what they're doing, but why don't they just say it? Okay, that to me is so much more sense. 2 pi r, take this area, which is h times dy, okay? You have to figure out what that is. That's given. You have to do it anyway. So that's the area, and you rotate that around, and so you basically have that as circumference around there. That's 2 pi r. 2 pi r h delta y. There it is. I don't know. Every time I struggle with trying to follow what they're trying to say, but that's exactly what's going on. And to me, that's just so much easier. I understand what they're saying, but boy, it's so convoluted. Okay. So you can approximate the volume of a solid by n such thicknesses. Of course, yeah, we're doing Riemann sum type things here. Of delta y's, height h of y I, and average radius p of y I. So the volume of the solid would be the summation of all those, and pull the 2 pi out, and then you've got that, and then that becomes better and better as your del, your largest increments approaching 0 to n's approaching infinity. The volume of the sphere then goes from the limit of those things to an integral. 2 pi times the integral from doing your y's, so from C to D, okay, whatever that range is, your radius function times your height function times your thickness. Yes, sir. Oh, you need the key. Yeah. No, I like it out last night before I left. I had this lab stuff. I did a lab last night, so yeah, I had to put the stuff back. So I liked it when I left.
Yeah. I was wondering if you meant tutorial on that screencast-o-matic. You use that, right?
Yeah.
We want to record this evening.
Well, record what?
You can record and screencast-o-matic.
Right.
So I'll use it.
Okay.
I got set up for it, but I never used it.
Okay. Do you have the long version, or are you limited to the 10-minute or something like that?
I don't know. I never used it.
Yeah. I think if you just go to that, it's been so long since I got it. I'm almost certain you have to get on the. He has a, what do they call it? A blanket thing for so many users, and they'll do for longer. Like I use it for hours at a time. But the freebie that everybody has access to is just limited like 10 minutes. Do you need the longer one or the?
I think we need the long one. Okay.
What you might do is check with Jamie Glass. You know who she is?
Yeah.
Okay. Check with her and see if you can get on that. They just have to put you on the site license is what I call it.
Oh, okay.
Because they have enough sites, no one much uses them. They have plenty of sites, so see if she can put you on that. And they have to give you something, but it's been so long, I don't even remember. I just use it. You know how to set it up. But but once they got you set up, then I can show you. It's pretty easy to do. Yeah, but I think you have to get on the site license if you're not already there. She may tell you you're already there. So
I'll try to get there before 2 o'clock.
Okay.
See what's going on.
Okay.
All right. I'll be right back.
Okay. Sorry about that, folks. So to me, that's the way to think of it. 2 pi radius height thickness. That gives you the volume. Okay. 2 pi radius is your circumference. H times dy is the thickness of that rectangle. Is the area of the rectangle. Okay. So let's see if we can do one. Find the this is the definition. Find the volume of a solid, a revolution by the shell method. Use one of the formulas. If you have a horizontal axis of revolution, then you got dy's. You got a vertical axis of revolution, then it's a dx. Because you're doing just the shell around there. So it's kind of backwards from what this method was. Okay. So the volume would be 2 pi times the integral from C to D of the radius of revolution, which is that's your radius from the whatever your axis is up to whatever that length is. Now, this has to be determined from your problem, the P of y. Why don't they call it R of y? I don't know, but they call it P of y. And then H has to be some function of y as well. Okay? Times your dy, 2 pi times the radius times the area. That gives you your volume. Okay? Vertical axis of rotation is 2 times the radius. Now the radius has to be a function of x now, not of y. Okay? And your h of x, that has to be a function of x too. And the dx, of course, is x. And 2 pi times the radius, that gives you your circumference of that thing moving around this circle. So you just get your height and your radius as a function of whichever variable you need it to be. That sometimes is the hardest part of the problem. formula is pretty easy. 2 pi r h dx, okay, or dy, whatever. Find the volume of a solid formed by revolving the region bounded by y is equal to x minus x cubed and the x-axis from 0 to 1. Now, I may not lock it up because I have to leave at 4 to go to the Birmingham campus on Wednesday, so if y'all are still using it, I'll just leave it open and try to remember to lock it tomorrow. Okay. Find the volume of a solid formed by revolving that region and bounded by that region and the x-axis between 0 and 1 about the y-axis. So you're doing around here, so we got to use dx's. That's nice because your y is already in terms of x. So I think what we got to do is draw a picture. And I'm going to hope they've drawn one. Okay. 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 Let's see. Is that the function of y is equal to x minus x cubed? I know 0, 0 is on there, and 1, 0 has to be on there. Put in a 1 here minus 1, that gives you 0. But in between, say 1/2, just pick 1/2 here, that would be 1/2 minus 1/8, which would be 3/8. So that would be the height there. So yeah, everything between here and here is going to be a fraction that this is going to be larger than that until you get down to 1, and then there's the same again, and then after that it goes way negative and never comes back. So yeah, we're just going to do that load right there, okay? Now, we're revolving around the y-axis. Now, can you imagine doing the disk method, or the washer method with this? You would have to do this minus that. That your washer would be dy's. Oh, and that would be hideous. It would be awful, okay? I'm not even sure I can think of how to do that, okay? But the shell method, this is just set up perfectly for it because the height is already given in terms of x. The radius is just simply your x, okay? You're revolving around the x-axis, so the radius is x. The height is given by your function here. Dx works perfectly. 2 pi times this times that. There it is. I mean, this is almost the prime example of one that would work very nicely. So let's do that, okay? All right. It would be the integral. You're doing dx's now. There's your dx of that shell. The 2 pi is out front, okay? The radius is x. The height is x minus x cubed. 2 pi radius, height, thickness. That's it. That's it. I left too much room with my dx there. Let's erase that and bring it in closer. Not lose any space here, okay? Now, probably the first thing you want to do is 2 pi. And, oh, we didn't do it, the limits. X going from 0 to 1, okay? 2 pi. Let's multiply through that through first. X squared minus x to the 4th from 0 to 1 dx. Okay? That's 2 pi. What's the antiderivative of x squared? Anybody? X cubed over 3 minus x what?
X squared. So it's going to be x5 over 5.
Perfect. Evaluated from 0 to 1. You can't have anything easier to evaluate than that, okay? That would be 2 pi, and when you plug a 1 in there, you have 1/3 minus 1/5. Plug a 0 in there, you get nothing, okay? Now, the only hard part here is doing least common denominators. It's the algebra part, not the calculus part. 2 pi times, what's the least common denominator? 15. And to make the 3 of 15, you'd have to multiply by 5. So you'd have to multiply the 1 by 5. That would be 5 minus 3. So that would be 2 pi times 2/15, if I could write, which would be 4 pi over 15. Okay? Which is not a huge area, because think of that. The peak is not much more than 3/8, so it's not going to be a very huge area. And, you know, just to approximate, that's about 12/15, which is about 3/4. Not a huge volume, actually. Not a huge volume as you rotate that around the y-axis. Let's see what they got. 4 pi over 15, good for them. Okay? Are we running out of time? No, not quite. Oh, yeah, we are, aren't we? Sorry. Let's see how they worked it. I think we did. The row of, I keep saying row, P of x is x, h of x is the function value, and there, I mean, there you have it. 2 pi times the radius times the height times the thickness. You got it. And that would be 2 pi is 0 to 1. Yeah. Oh, I thought you were going to say something. Just like we did, except they reverse the order. Isn't that grand? You know, minus x to the 4th plus x squared. That makes a lot of difference. And that would be a minus x 5th over 5 plus x cubed over 3. Evaluate 0 to 1. Minus 1/5 plus 1/3 is 2/15 times 2 pi is 4 pi times over 15.
Can you go back to what we did?
What's that?
Can you go back to what we did? Yes.
Yeah. Okay. Oh, I'm sorry, I did not did it too soon. Okay. Now that was example 1. We didn't do example 2, and they don't do it. It doesn't look like in the slide set. So we will do example 2 first. We'll lead off with that tomorrow, and or tomorrow, Monday, and next time we meet, yeah, and meet a week from the day before yesterday. Okay, something like that. Homework exercises here. I think you can do 3 or 5. No, any of the odds 3 through. I would do either 3 or 5. They should be at calcchat.com, and then any of the other odds 7 through 11. And they're all at CalcChat, but 7's at CalcView. I think you can do 13 or 15. They're all at 13 through 21. I'd say do 13. That's a pick. No, 13 or 15. I'll back up it several times here. Then do any of the odds. They're at CalcChat. Then do any of the odds 17 to 21. They're all at CalcChat. 17's at CalcView. Then do let's hold off. Well, try to do 23 or 25. They're both at CalcChat. 23's at CalcView. And we'll stop there and pick up the rest of those next time. Okay. Good deal. All right. And have a good weekend.
Yes,
Of course, working calculus problems will make it good.
That's right.
Okay. Anyone need this a little longer?
Thank you.
Okay.